a step function, or unit a step function. Step function. So it's a piecewise defined function that will be defined in different bracket. So this is going to be officially the definition. We are going to use a number of a base, we call it. So that number would be C. This notation is standard, so you have to use this one. Suppose C is a non-negative number. It's not zero, it's not negative. C is a non-negative number. Okay, if this is going to be the case, then the unit a step function with this base. The unit step function. Step function. Unit step function. It's going to be denoted by. Denoted by. Yes, the notation. The notation would be this one. UCT. UCT. So C is going to be the base that we're going to have, and this is okay a function of T. There's a notation in your book, which is a very bad one. Okay, but this is more standard one. I'm not going to use that one. Notation in your book is instead of UCT, they go with something like, okay, this is in your book. Go with something like U of T minus C, something like this. This would be confusing because we're going to do something to this one other than, everywhere you go into the different problem of the differential equation, this is the one, okay? UCT. So be careful if you're using, okay, different notes or different, okay, different books, but I'm going to use this one, the standard. Okay, UCT, and it's going to be defined by, and is defined by, it's a unit, a step function. It's a piecewise defined function. You see, we are going to partition the domain. This is going to be UCT. UCT is going to be equal to, we introduce the function when the T is less than C, when the T is greater than C, okay? So it's going to be denoted by, we choose it to be 0 if T is less than C, okay, and is equal to the 1 if T is going to be greater than equal to. That's it. Okay, now there is going to be kind of a complement of this one that's going to be also used, so you better make a note of that one as well, okay? Note that. You see this function is started with 0. Sometimes we may have to switch this one. 0, 1, we may go with the 1, 0. And then we use the complement of this. So note that. At this function, 1 minus UCT. 1 minus UCT. Okay, if you put it on the top there, this is now going to be, you see the top part would be 1 because this is 0. Okay, 1 minus 0 would be 1. So there's going to be 1 when T is less than C. And over here, 1 minus 1 would be 0. So make a note of both of them. So, sorry, this must be bigger than C here. Less than C, greater than C, okay? So it's going to be the same thing over here. And this is going to be when T is greater than equal to the C. Okay, but we go officially with the first one as a UCT. And the other one as a 1 minus UCT. You can graph it to see it. Okay, it's a piecewise defined function. If you want to graph this function, this is it. I'm going to graph this one, okay? And so you have a y equal to the 0, y equal to the 0 will be part of the x-axis, okay? Y equal to the 0, but you want it up to the C. C is going to be a positive number, so you identify the C here, and you make a hole. Okay, so it's going to be C. So this is going to be when T is less than C, this is going to be a function. Okay, when T is less than C, the function is going to be part of the x-axis. Okay, and when T is greater than 1, the function is y equal to the 1. And if this is going to be 1, if this is going to be the 1, And if you create the y equal to the 1, see, this is going to be, if this is going to be y equal to the 1, but your function is defined when t is greater than c. So you are going to have only this part. Okay, so this is going to be the function. Okay, so it's going to be a function when t is less than c is part of the x-axis, y equal to the 0. When t is greater than c, is going to be y equal to the 1. Okay, if you have done a very good calculus 1, in that we did have something that we call a greater integers function, usually denoted by this one. See the bracket function. This is also used in calculus 1. So the bracket function is going to be the integer part of the number. So if if you pick a number, if x is integer, the bracket is going to be just 2. And if the number is not an integer, if you have 2.5, 2.4, I'm going to consider the largest integer, which is going to be less than 2.5. So the largest integer is going to be less than 2.5 is going to be what? Is going to be 2. So probably, the calculus 1, this is the way we denote this function. We call it 0 when x is between 0 and 1. Because if you consider all the numbers between 0 and 1, greatest integer part of those numbers would be 0. Okay, because you are not going to consider the 1. And if you go with 1 and 2, 1 and 2, all the number between 1 and 2, if you take the integers part, would be 1. And then you continue, and that gives you, so this is it, that gives you 2. So 0, 1, 2, 3, 4, 5, 6. So if you graph it, it's going to be like you have here. You have these steps, stairs, if you like. And this is the way we think about those type of functions in calculus 1. But this is a very special one. Just you are going to be taking 0, 1 on it. So that would be, so these functions are right. Okay, your first job. We give you some other functions. So if you can write it down in terms of the UCT would be fine. Okay, because you are going eventually to deal with the Laplace transform of these functions and all other functions. So to get this experience, okay, so that would be our first question, algebra, working with this. Okay, I give you the function, you write it down in terms of the unit step function. So I would like you to write, write each function. Write each function in terms of a unit step function. Okay, in terms of unit step function. The function, I'm going to a couple of them that we are going to use. It's not bad to get this experience. Okay, the first one is this function. We have f of t is equal to the 0. If t is going to be between 0 and 3/2. And this is going to be equal to the sine t. Sine t if t is going to be greater than or equal to the 3/2. You see, this is the given function, and you want to write it down in terms of the unit step function. You see, look at this function. So your function is going to be a function of 0, 1. Okay, it's going to be 0, 1. So in this case, you do have the 0 here. So in order to write it down as a unit step function, you need a 1. So just think about it, how we're going to break this function in 2 parts, okay, or factoring something to make it as a unit step function, okay? If you like to have the sign out, if you like, okay, in this case, you can factor it if you like. If you factor the sign out, so the top would stay 0. 0 times sine t would be 0. At the bottom, I will give you 1. So one way to do it is you may add, subtract, multiply. This is the operation that is going to be. So the solution is going to be, you can rewrite it. Okay, you can rewrite f of t. You see, this is the f of t given one. It's a kind of factoring the sine t out. So if you multiply by the function, sine t 0 would stay 0. this would becomes 1. Because now sine t times 0 would be 0, sine t times 1 would be sine t. Okay, and this is it, and this is going to be what? The range are going to be as is, or the domain of that function. Now this is going to be unit step function. What is this one? How do you write it down? In terms of the unit step function,
C.
see the base is 3 pi half. So this is going to be equal to UCT is going to be equal to the sine of t, okay, sine of t, u of 3 pi t, u of 3 pi t. So in short, this is going to be the function. So that would be easier to handle. Get these through these numbers. So you should be able to read it as it's given to you. This is mostly the format that we're going to have. Now, in a minute, today, by the end of today, you should be able to find the Laplace transform of this function. Okay, so that's why we change it to this format. This is one idea to just factor it out. Any question? Let's have another one. You know these type of operations. So the next one is going to be, how about this function? I have f of t is equal to the cosine of t. Cosine of t when t is less than 2. And then this is going to be cosine of t plus sine of t. Okay, when t is greater than or equal to 2. I'd like to write this one as it's a combination of the unit step function. Again, think about it. Unit step function is 0, 1. So just think about it, how we're going to get rid of these. Yes, any suggestion?
We're gonna need 2 u's. So like one is like 1 when it's above 2, and then we have another u of something when it's below 2.
Yeah, we may change it to the different combination. Just think about it, how we're going to create those 0, 1 that you need over here.
U of 2 times cosine t plus sine t, and then u.
Now let's break it first, one by one, to see what you need. You have to get rid of this cosine first.
So pull this cosine
See,
out.
it's a cosine. So what we can do is, we can pull it out, but you have to add it this time. Because you want it for the first part and you want it for the second part. Okay, and you want the 0 on the top, remember?
Okay.
You want the 0 on the top, so you have to pull out the cosine t. Okay, so one way to do it is this one. So it's going to be f of t is equal to, so you subtract cosine t here, you pull it out. If you pull it out, that gives you cosine t plus, now your function would be of this form. That's what? 0. Because cosine t plus 0 would be cosine t. And the sine t here. Okay, t less than 2 and t greater than or equal to 2. Now the rest, you have you put out the sine t as a factor, and the leftover is going to be unit step function. So this is going to be equal to the cosine t, okay, plus sine t. So that gives you 0, 1 that you are looking for. That's it. This is the unit step function at the base 2. So the result is going to be cosine t plus sine t times it by u2t. So that will give you f of t. And when you do a couple of them, then you get the idea. Okay. You'll be able to break it yourself. Okay. So u2t sine t, or you just write the sine derivative. Any question? So this is going to be, we are going to have a various version. Let me give you another one. This next one is going to be used again. Okay, number 3. Number 3, we use this one quickly. And how about this function? f of t is equal to, get the 0 here when t is less than 2, and you get the t minus 2 squared when t is greater than or equal to 2. So it's very similar to the one that we have. You can factor out the t minus 2 squared. That will be 1, and then you're done. Okay, solution. So you write it down as f of t equal to, you pull out the t minus 2 squared as a factor, so that would be 0, t less than 2. This would be 1, t greater than or equal to 2. When you multiply the top with 0, the bottom one as you want. So this is going to be simply f of t is going to be what? It's going to be t minus 2 squared. T minus 2 squared and the u2t. So this is how we are going to have various combinations of this type of function. Okay, any question? Now, the next question is going to be, of course, we are interested in Laplace transform. So what is going to be a Laplace transform of the unit step function? I'm going to prove it for you. It's a nice formula to see it, and you already done it almost. Okay, but you can see it. So this would be the new formula that you have to add to your terms, if you like, on the differential equation that you saw on your quiz. When we get to the next test, we give you two. One of them would be ordinary one. The other one would be involving this unit step function. Okay, so the idea is going to be, what is the Laplace transform of a unit step function? Okay, let's go for it. The Laplace transform of the unit step function. Unit step function. That's it. Let's prove it. Let's find out. Okay, this is it. So, so what we are going to do is, suppose you have this unit step function, uct is equal to the 0, t is less than c, and is equal to the 1, then t is greater than or equal to the c. Okay, so what we are interested in, Laplace of uct. So go with the formula. It's 0 to infinity. Okay, 0 to infinity, e to the negative st uct dt. The definition of that. Okay, but since it's a piecewise defined function, so you have to break it. Because the function is defined when t is less than c and greater than c. So we are going to break it in two parts. We go from 0 to c, t less than c, 0 to c, okay, e to the negative st uct dt plus c to infinity, e to the negative st uct dt. But when you are between 0 and c, t is less than c, the function, unit step function is 0. And over here, the unit step function is 1. So you end up with what? You end up with finding c to infinity. C to infinity, e to the negative st dt. We'll work on this one. Definition of a limit and integration. Okay, so I'm going to find it. So it's going to be equal to the limit equals to infinity. Okay, and integral of c to b e negative st dt. Integrate, so the limit of infinity. So it's going to be e to the negative st. Negative would be negative s. Okay, negative s, but when t goes from c to b. To simplify it, I can bring it down. So it's going to be the limit of e goes to infinity. So this is going to be 1 for the negative 1. Negative 1 over s e to the negative st So going from C to B, substitute. You substitute with the limit of -1. If you put the B, it's going to be S e to the negative SB minus -1 S e to the negative CS. Replace the T by CS. Sorry, I bring it down. This is positive. Yes, it's plus. And this is going to be plus e to the CT. Okay. You substitute for T e to the CS. Okay, because you place the T by C. So the first one is a -1 over S e to the SB minus -1 over S e to the CS. S e to the CS. Okay, now B goes to positive infinity. When E goes to positive infinity, this, the denominator would be positive, so this would be 0. Okay, this would be 0. And in this case, there is no B. So the answer would be simply negative, positive. So that gives you 1 over S e to the CS. In order to remember it, we usually write this one in the negative form. We move it up, e to the negative CSS. So this is the formula that you have to memorize or just use it in your table, that the Laplace of UCT is going to be e to the negative CS divided by S. This is the Laplace transform of the unit step function. Very popular, especially like the other way around, Laplace inverse. So equivalently, you have the Laplace inverse. So Laplace inverse of e to the negative CSS is going to be UCT. And when you solve the differential equation, this is the one that you're going to use. Most of them. Okay, so add it to your combination. Usually write it down as is. Leave that one up there to be able to work with. Well, that's it. That's the Laplace transform of the step of function. Let's get some example. Any question? Don't memorize it. You are not going to be asked to prove because we are going to have some nice proof over here. And we give you one of them in your next test. I'm going to let you know which proofs are. Okay, let's get example. So this is how you are going to use it when you want to solve the differential equation. Okay. The format, the direct one, find the Laplace inverse, and indirect one, find the Laplace. Direct one, find the Laplace transform. Okay, so let's do the find the Laplace transform. Laplace transform. Laplace transform of each function. Each function. This is the way you are going to question your into the test. Finding the Laplace transform of this type of function. Okay, there you are. This is it. The function is. This is the function. F of t is equal to. We give a combination of this function. U1 of t plus 2u3 of t, okay, minus 6u4 of t. We say a combination of unit step function. We use that formula for each one of them one by one. Because the Laplace transform is linear, so as you did it before, so this is going to be the situation I'm going to have, the solution. So what is going to be Laplace of f of t? Laplace of f of t is going to be Laplace of all of them. You that you can break it into parts. Okay, so I'm going to break it. It's going to be Laplace of the first one, Laplace of u1t. That's 2. That's 2 Laplace of u3t. Okay, minus 6 Laplace of u4t. So substitute for all of them. You proved it just. The Laplace of UCT is e to the negative CS over S. So this is going to be equal to e to the negative CS. C is what? So negative S over S plus 2 times e to the C is 3, negative 3S over S minus 6 times e to the point, the base is 4, e to the negative 4S over S. That's it. So, you know, we can put them together. It's the way we write it down. E to the negative S over S. And this is going to be plus 2e to the negative 3s over s. And this is going to be minus 6e to the negative 4s. Okay, we accept it, but it's easy. You can, if you want, you can put it together because they're all like fractions. If it's going to be like fraction, we simplify. Otherwise, you leave it as is. So it's going to be s. The top would be e to the negative s plus 2e to the negative 3s minus 6e to the negative 4s. Okay, so that would be the final answer. If the numbers are going to be different, just leave it as is. In this case, we simplify. Okay, so that's one version. Any question? Quickly, we have it the other way around, especially this problem. See it later on. So, example, I'll find the inverse Laplace function. Find the inverse. You find the inverse Laplace transform of this function, okay? Of the Laplace transform, just inverse. Laplace transform. This, okay, the function is f of s. It would be very similar to the one that we did. Okay, so let's give you this one, e to the negative s plus e to the negative 2s minus e to the negative 3s and minus e to the negative 4s over s. As soon as you see it, you find out that they must be given in terms of the unit step function. So you break this fraction into partial fractions. Okay, all the numbers are s, then you apply the Laplace inverse. Okay, so this is the way we do it. Solution. So the solution is going to be what's going to be the Laplace inverse of fs. Okay, so you break it. It's going to be Laplace inverse of. So that would be e to the negative ss plus e to the negative 2ss minus e to the negative 3ss and minus e to the negative 4ss. That's it. And you know that Laplace inverse is linear. So you expand it, it's going to be Laplace inverse of e to the negative ss, okay, minus plus Laplace inverse of e to the negative 2ss minus the Laplace inverse of e to the negative 3ss minus the Laplace inverse. You can do it right away, of course. Yes. You can look at it, you know, and just do it. This last line. Now, to compare it with the formula that we have, e to the cs, e to the negative css is the Laplace transform of UCT. So in this case, this is going to be equal to, the base is 1 now. So that gives you u1t. Okay, that gives you u1t. The next one, the base is 2, u2t. Okay, so that gives you u3t. The last one would be u4t. So that would be, you know, f of t, or just the Laplace inverse of the given function. Inverse of f of s. And then okay, so this is the basic part, and the way we are going to do it. Now, the way we are going to use it in the application problem is going to be, we have two different versions of it. For the application problems, that would be very useful if you have it. Let's just give you the, like to give you the theorem. I may prove it later for you, okay? Let's see it. So this is the real one, really. Quite interesting theorem. This theorem, they call it in your book, they call it translation theorem. Translation theorem, we are going to have two theorems connected to the unity step function, and we call them translation type 1, type 2. Don't bother about the name. Understand it and use it. So why we call it translation? This is the one. Look at this theorem. Again, it's to prove, but let's have it and then next time. So this is the case. Look at this. If Laplace of a function is given to you, see this one? This is going to be f of s is given or exists. Given or exists. With this condition for s, the one that we use is going to be bigger than a specific number, and the a is positive. And c is going to be that positive number that we use. C is a positive number. Positive number. Okay, with this condition, then you are going to have this formula. Quite interesting. The formula is this. Laplace of UCT. Okay, UCT times a function. And your function we usually write on f of t. And we are going to shift the t into the t minus c. That's why we call it translation theorem. So it's going to be UCT f of t minus c. F of t minus c. This would be simply, see if this is given to you and you want to find the Laplace transform of this one, because of the UCT, you end up with the quotient with the factor of e to the cs. Then this function, you see, the Laplace of f of t is already given to you. So this is going to be simply Laplace of f of t. Okay, so UCT, you have it. UCT would be e to the negative cs. Then you have to only find the Laplace of f of t. Or you can write it down in different format, or after one say Laplace of UCT f of t minus c is simply e to the negative cs times f of c. You see, this is going to be the formula that we call it translation theorem. And it can be proved easily, just integration by parts. I prove it for you later. But the way we are going to use this one is the other way around. The other way around means equivalence. Equivalence. If this is given to you, if you have something like e to the negative cs fs, this function is given to you, and it's going to be quite a lot. And you want to find the Laplace inverse of this function. If you want to find the Laplace inverse of function, because of the e to the UCT, you write one step function, UCT. Then what you are going to do is, this fs that's here, you are going to find the Laplace inverse of f of s. Laplace inverse of f of s would be f of t. We write it this, see? We say f of t. When t is going to be changed into the t goes to t minus c. In this form, it's, or if you like, or Laplace inverse of e to the negative cs fs would be simply UCT f of t minus c. In this format is the one that we're going to use it for differential and differential equation. So this means if you want to find the Laplace inverse, you try to solve a differential equation. At the end, you want to find the Laplace inverse. You will see a number of these e to the negative cs. So what you do is you ignore the e to the negative cs. You find the Laplace inverse of that function, which can be done by the table or other method that we did. Then when you want to write the final answer, Whatever you got the f of t, you change it into the f of t, t minus one. For example, if c is pi, and you find the Laplace inverse of your function and you arrive at sine of the t, you have to change it to the sine of the pi minus t. I'm going to work in this one next time for you. It's quite interesting. It's not going to be something easy to handle. It's something extra that you do whatever you did today, for example. Same problem, I draw one of these using the step function. First, you ignore it. You go and find your f of t. At the end, you come back. Oh, the f of t, I change it to the t minus. Then we can solve it.